In this lab practical, we're given three variables: mass, velocity, and initial height, and we want to use those to measure the range that a projectile goes. So first thing we need to do is determine whether all three variables have an effect on range. So first, I launch with a pumpkin. Range, in this case, is the distance from where it was launched in the x direction to where it landed in the x direction. So I'm using a measurement tool. It looks kind of like a tape measure. I'm putting it right under the cannon along this line right here and measuring out to the pumpkin at 21.56 meters. Then I'm going to change it from a pumpkin to a car. Now it's going from 5 kilograms to 2,000 kilograms. When I launch again, in theory, it falls in the same place because there's no air resistance. That means no matter what I do with the mass, it'll give me the same range. We call this having no relationship. You cannot pick mass as a variable later on in order to do your graphs because mass is not having a relationship with range. That's because in theory, mass has no effect on your acceleration due to gravity, and therefore it would not change how far you fall or how fast you fall. So now let's reset it. And what we're going to do is we're going to change velocity. Velocity is a potential independent variable. If I launch it at 4 meters per second, wow, that didn't go far at all. It only went from here, well, it went like 5 meters. If I go faster, from 4 to 8 meters per second, oh, that goes much farther. Instead of 5 meters, now it goes 11 meters. So I'm going to keep going. How about like 4 to 16? 4 times as fast. Definitely goes farther. Okay, so I know at this point that even without collecting exact precise data, that increasing the velocity increases the range. I would check the increases box on the lab practical, and that is a variable I could study when I'm looking at my data taking. So let's reset one last time. So let's say I want to do height versus range. Keeping the speed constant and the same mass, I can do different heights. And I see that increasing the height increases the range. I even hit that target once. So height is another potential variable. Increasing the height the cannonball is launched from increases the range. So now let's go collect data. Let's say that I collected data for height versus range by modifying the height from 1 meter, then measuring the range it travels. In this case, that's 6.7 meters. Then I would keep increasing the height, keeping my angle at 0 degrees if you can, keep increasing the height, and measuring the new range. 9.54, and then we collect data. So now we take our 8 data points. The reason you need to take enough data points is if you initially plot this graph, it looks something like this. And on the first 3, you're looking at it and you're like, oh man, that looks like a linear function. But the more and more data points you plot, you realize that it starts to turn. In fact, this is a square root function. As height goes up, range goes up, but it definitely doesn't do the whole direct relationship doubling here. Notice that when you double the height from 1 to 2, it definitely doesn't double the range from 6 to 12. When I triple the height from 1 to 3, it doesn't triple the range from 6 to 18. It's less than that. This is a square root function. The name of this relationship would be a square root. And the equation for a square root is y is proportional to the square root of x. So I would take the number or the quantity on the y-axis, that was called range, and set that proportional to the square root of height. But make sure you go back here and go to the symbols that were used. Go to the symbols that were used in this spreadsheet. In this case, it used range as x is proportional to the square root of h, height. That's my mathematical equation's name, square root, and the actual equation itself. So I'm going back now and I'm going to collect data for velocity versus range. And fun fact, guys, I found a better tool for this. So I'm going to keep the height the same. The 10 meters initial height is going to stay the same. But I'm going to increase the speed at regular intervals. So let's say I do a speed of 0. Well, that means its range is 0, goes straight down. I found this tool that lets me just measure the range. So all I need to do for that is go to one of the dots highlighted along the trajectory. So from a initial height of 10 meters, it had a range of 0 meters because the velocity was 0 meters per second. So data point 1, 0, 0. Data point 2, 4, 5.71. Data point 3, 8. And 11.42. So you'll see that there's a pattern emerging here. We're going to collect this data. So this would be 12 meters per second, 7.13. I happen to like how this just looks. We can see that faster objects have a larger range. And since I'm doing it at even velocity increments, I can even see how far it goes when it's over here. So now we've got our data. We've got our velocities and the corresponding ranges. Someone asked me the other day, they had forgotten to take 0, 0 as a data point. No big deal. And they had done their graph and it looked something like this. And they're looking at it and they're like, oh, Ms. Pasega, does this mean it's not a direct function because it doesn't go through the origin? No, I would guess this is a direct function. Even if I hadn't taken the 0, 0 data point here, I can see that if I extrapolate my data backwards, going through the origin is probably pretty sensible. And since I took enough data points, I took more than 5 data points, that is plenty to establish a trend. Now, quick thing, since this is the easy graph, make sure we do things like label our axis in terms of both the label and the unit. Same with the top of a table. Label, velocity, range, unit, in order to get full credit. Make sure your line is your best fit line and that you plot your data points accurately. Okay, so I know this is a direct relationships. That's the name of this relationship. And a direct relationship means that y is proportional to x. Well, that means if I take what's on the y-axis, that's the range. And what's on the x-axis, that's the velocity. This means my mathematical equation that fits for this data set is range, whose symbol is x, is proportional to velocity. So then, let's take a second to look at all the possible functions this could be. First off, if you're getting a no relationship function like mass and free fall acceleration, a function that when you plot it looks like this, please don't use that as your example. If there's no relationship, then there's no equation I can write relating the mass and the free fall acceleration. If you choose a no relationship one, you won't be able to get full points. So let's say at the end of your experiment, you've taken your data and you make a graph that looks like this. This was a lab we did before. And in this lab, we did net force versus acceleration. Picture to yourself like we pulled people on a cart, going faster and faster, because it had more and more force attached to it. If you pulled with more force, it accelerated more. This was a direct relationship, just like the one we just did. The name of this relationship is direct, and that means y is proportional to x, or in this case, the y-axis is acceleration, the x-axis is net force, and so my name of equation is direct, and my equation itself looks like this. You just don't want to leave it in terms of x and y. So here's another law we've done. We also did mass versus acceleration, and it got a graph that looked like this. This might be something like taking a 1 kilogram block and pulling it with constant force, and then adding more and more mass and measuring acceleration. This relationship is called an inverse relationship. What it means is if you double the mass from 1 kilogram block to a 2 kilogram block, you get half the acceleration. So I'm putting an easy example of maybe it goes from 8 meters per second squared to 4. Doubling the mass cuts in half the acceleration. So the name of this relationship is an inverse, and an inverse relationship means y is proportional to 1 over x. And I would write that equation as acceleration A, that replaces my y, is proportional to 1 over m. So I would write the name as inverse, and the equation itself would be acceleration is proportional to 1 over m. What about this one? So we've had a no relationship, direct, inverse. What about speed versus kinetic energy? An object with no speed has no kinetic energy. And the more speed you have, the more kinetic energy you have. But this isn't the same as a direct relationship. This is called a square relationship. Maybe your experiment is something like taking a baseball and throwing it faster and faster and faster, and measuring how much kinetic energy it has right before it hits the bat. In a squared relationship, y is proportional to x squared. The quantity on the y-axis is kinetic energy. The quantity on the x-axis is speed. So kinetic energy is proportional to v squared, which we know, because kinetic energy is equal to 1/2 mv squared. So far, we should know no relationship, direct, inverse, and square. Notice that as I'm making all of these graphs, I always label the axes with name and unit at least. Sometimes you'll notice I also include the symbol of the quantity. Right. So last two. Range versus height was one we just did. Our graph went through 0, 0. It looks something like this. And remember to take like at least 5 or so data points, because your first few make a straight line. You don't notice it's nonlinear until you get your ladder data points. So in this case, this is a square root relationship. It increases, but it doesn't square. It doesn't curve up like a normal parabola. It curves down like a square root. In fact, if you graph this in Quick Graph on Physics Aviary, you can actually see that they give examples of what each function looks like. That could be a good tip, because you are allowed to use the other Physics Aviary programs as you go. So On the y-axis is range. On the x-axis is height. So I would write this equation as x for range is proportional to the square root in height. Now, if you have trouble, you're looking at it and you're like, I don't know what to replace y and x with, keep in mind that it'll be on the front page of your lab practical. I have to tell you the symbol of anything that's not obvious. So for instance, if it's something like, I don't know, resistance, which you and I have never done before, I would have to tell you that resistance is R and measured in ohms, somewhere in the context of the front page of the lab. So our last relationship then is an inverse square. This one people are notoriously tricked by because it really, really, really looks like an inverse relationship, but it is not. It's steeper than an inverse relationship. A good check if you think your relationship is inverse square is to ask yourself, is this something that spreads out uniformly in a circle? Some examples of an inverse square law include like how gravity from the sun affects all the space around it, spreading out in a circle in all directions. But when we originally did this in class, we also did this with a light bulb, light spreading out equally in all directions. I gave other examples like sound. Because sound spreads out equally in all directions, a person that is twice as far away actually hears a quarter of the sound amplitude. So that means when I have a gravitational force of 100 newtons, if my two objects, object A and B, were placed twice as far apart, it wouldn't give me 50% of the force. It would actually only give me 25% of the force. This is because as this spreads out uniformly from our picture over here, the field has to spread out over a greater and greater area. When you're close, all that intensity is just along one area. But if you're twice as far away, the same intensity has to spread out over a greater area. And since it's a much greater area, 4 times the area, you actually have a much steeper line. An inverse square relationship looks like y is proportional to 1 over x squared, or in this case, gravity is proportional to 1 over r squared. Last thought, guys. So if you're going through these and you're like, I would like more extra practice, all you need to do is go to Physics Aviary or go to PhET here, go to the simulations that open HTML5, and pick any one you want. I prefer if you go pick some of the physics ones, such as the capacitor one that we've done before, the charging in fields. Pick variables and see how they work together. So, for instance, if you went to the gravity force lab, you could figure out the relationship of how does mass here relate the force measured up here. So by increasing mass, you could take data, make a graph, and determine a relationship. Same with changing the radial distance. You could change the radial distance, measure the force, make your graph, and determine your relationship. So I don't need to make lots of extra practice for you. You guys can make some extra practice on your own, and I will see you for your exam date. Best of luck.